Hi, Charlie.
Hi, Jorge. How's it going?
How's it going? Yeah, fine, fine. Just had the notification and oh, yeah. Early, I think.
Yep. So you've been doing some more analysis this time on the Hill of Towie dataset.
Hill of Toe. Yeah. I'm just yeah. First, I'm looking at the data and just playing with that because this is the typical problem where you have a lot of missing values and stuff, and you have to complete that. I mean, crazy. Yeah, but it's cool. I mean, it's nice. I think yesterday or when was that? I mean, this week I published something in LinkedIn because I grouped the family of turbine. Really interesting just seeing a clustering method there.
Yeah, I think it's good, and I like that you're posting things up about what you're doing because it's really beneficial for like people that are releasing the data to see it being used and
to see things. And when I do the post, it's like an opportunity to summarize. Because I mean, bullet points. Okay, this works like this. I did this, and this is the result. It's like
you write good things for your internal
to
tracking.
remember.
Yeah,
to remember. Yes. It's like an exercise for me. Like when you write a paper or something like that, you always an exercise of putting things in order because everything is so chaotic. And then what I did is that first step, second step, and the result of this. Okay.
Yeah, works, and then you realize what you've done wrong, and you're like, "Oh, actually, I need to redo that step." And,
exactly. Yeah.
Oh, that's cool.
People is arriving.
Yeah.
I think. Yeah. It's mute by default when you enter the chat room. I think.
Yeah, we'll give people a bit of time to join as usual.
Today it's about the
today we're
data some data, some SCADA data set or something like that.
Yeah, so releasing a new data set and also a new challenge for people to work on. Although we'll have to we've still got to get all the data in a format to use, but I'll give a background to what the challenge will be. And then actually Daniel's, who's just turned on the camera, fingers crossed he's got an analysis to share to give you an idea of what you can do with the data.
Okay, let's see what it's all about. A new data set, no? Cool.
Yep.
Oh yeah.
Hello, Charlie.
Hey, Daniel.
Hello.
Yeah,
Daniel.
I missed the first part of the introduction. What was the latest, really?
Yeah, no worries. I'll just kick things off now. I think we've probably got enough people on the call to start. Let me just check. Am I recording? Yeah. So just everyone knows this call gets recorded, and then I'll post it up on the WeDoWind website or community space. So for those of you who don't know what this call is about, you've just randomly joined something. This is the open data exploration space. And so the work of this group is to look at open data and what can be done with it, and to encourage people to do analysis together and collaborate on like open source code and these kind of projects. So in the space, we run a few challenges. So we've previously run a challenge on running an operational energy yield assessment using data from Kelmarsh and Pembrokeshire wind farms. We've done a challenge on static yaw misalignments using data from Kelmarsh wind farm. We've done a challenge on predicting wind speed at a turbine using just data from other turbines. And then today, we're going to start off a new challenge. It's going to come in steps. So this is kind of like the pre-briefing of the challenge, which is using data from a research turbine at Ost, Eastern Switzerland University of Applied Sciences. And that turbine has higher frequency data that we can use. And then, yeah, the way we're going to run this challenge is a bit different to the others. So previously we've run challenges where basically people just go away and do their own analysis and then come back and report. For the predict the wind speed challenge, then actually we did it on Kaggle so that people could contribute their code and share their code through Kaggle. And in this case, we're going to try and use Renku, which is a data science platform. And hopefully Daniel has a demonstration of how that's going to work.
No, but I mean, the Renku, when we were trying, it didn't work out because we couldn't afford the space. I mean, the resources that were available to us were not enough to run it. So what I have is on my local machine, but we could do it together if it works.
Yeah, that works as well.
Mm-hmm.
Yeah. Just before I do that, though, or rather hand things across to Daniel, I'll just share my screen because I also have another announcement. So earlier this year, Res released the data set from Hill of Towie. Just last week, 13th of August, 2 weeks ago, more or less. Then the two Cubico data sets, so Pembrokeshire and Kelmarsh, have been updated as well. So we now have data up to the end of 2024. For Pembrokeshire, then the data's a bit more fragmented than usual. And I understand that's because there was a problem with one of the wind turbines and like data communications from it. So the file was corrupted. So it's broken down a bit further. So we've got like months, February, March, Q2, Q3, Q4. But January's been excluded because the data was corrupted.
Okay.
And that's also so that's Pembrokeshire, and then also for Kelmarsh, then the data's been updated as well in the standard format. In fact, it looks like we've got some additional signals because our size of the files has gone up. But now we've got data for 2023 and 2024 as well. So that's now available. Okay. So to introduce a new challenge, say this. Let me stick this. Have I got the chats? So if you have not previously accessed this page before, which actually I'm guessing you all have because you've managed to find the meeting invites that I've put in the chat. Events, live event happening now. So I think most of you have probably joined from here. And then we've got future events coming up as well. All events will now be done through this platform. So make sure you've got the invite and you can download the invite to your Outlook calendar as well. And then on the challenge page, so there's previous challenges 1, 2, and 3. Well, we've now got challenge 4, which is on static yaw misalignments, Mark II, because it's the second attempt at it. And here you can find the link to our new data set, to OST University, to NRAR as well, because we're going to be using the OpenOA tool, at least for part of the challenge. And then also the Renku space. So all those links are there. And since we started with data as well, just to highlight, this data is also stored on Zenodo, similar to Kelmarsh, Hell of Towie, and Penmanship data. So access is available to everyone. Just check. Yeah. Okay. So yeah, the new challenges, we've got this SCADA data from the Aventa AV7 6 kilowatt research turbine. It's at a 1 Hertz frequency, got a number of signals. And what we've done with this turbine is we've applied static yaw misalignments, known static yaw misalignments to the turbine. And then what we want to do is, with a training data set, so for some known static yaw misalignments, check if we can determine what they are. And then after that, we'll have a new set of data released, which we will probably provide the timestamps for when the changes to the static yaw misalignment have been done. But we'll keep hidden what those static yaw misalignments are and leave it up to people to try and determine what they are. Yeah. So with that, any questions before I hand things across to Daniel?
So how many minutes do I have?
As long as you like. And so I say as long as you like, as long as finished by the end of the hour.
All right. Good afternoon, everyone. Well, so as Charlie already introduced me, I'm Daniel. I'm a PhD student here at OST. Well, so with this challenge, as he said, what we wanted to do is to see whether our readings or signals from the turbine at our set misalignments would coincide with what we would be able to calculate with using the OpenOA tools, really. So with this particular data set that we published, it has yaw offset of 0 and another at 6. So we combine those two data sets, yaw offset, and we want to see if applying the OpenOA method, we would be able to get our set yaw offset. So we started by just reading our data. So SCADA 0 is just our signals when our offset was at the default setting 0.0, and then we did same when it was 6. So for to use the OpenOA, you need to create a plant object, and for the plant object, you need the asset data frames and those kind of stuff. I wouldn't bore you with that. You could look at them. And so that's exactly what we did. And then this is just a plot of where the wind turbine is. And so these were the signals that we had, very weird from our turbine. So this is when the yaw offset was set at 6, really. And so we needed to apply certain filtering. I mean, maybe for the technical parts later on, Charlie could explain it more. But so from the distribution here, when the pitch angle against the wind speed, we know that the power curve should be around this side where we have the pitch angle less than 40 degrees. So we had to do some filtering. And whatever we did here was just using the OpenOA notebook. We didn't do any further investigations or anything. So we ran with the basics. So one is for when the year offset was at 6, and the other one is when it was at 0. So here is us trying to do some filtering. We tried a couple of them, but we settled with this. It's still not as smooth as we would want, but for trial purposes, we settled with this particular one. And this is for the other signal. This, we were just considering ways of filtering the power curves and comparing what the OpenOA method does, which is mean absolute deviation against using standard deviation and stuff. But I mean, I wouldn't bore you with this. And so yeah, here is where we actually ran the static yaw misalignment. So we started off creating the static yaw misalignment objects, and then we use these parameters to run the simulation. And at the plant 6, these were the results we had. Well, it looked a bit weird. We're still investigating why, but maybe once again, Charlie could be able to explain to us. So we realized that, I mean, when we expected it to be at 6, we had the overall mean or misalignment to be 9.6 for when we had set our yaw offset to be at 6. And we realized at from 5 going, it increases like at range speeds of 5 to 6, there is an increase, but as you go beyond 6, it starts reducing. And that was because our wind turbines rated speed is around 6. That's at least what the experts told me, really. And for the one where the yaw offset was at 0, this is what we had. We had 11.0, really. And you would have expected the one at 0 to be slightly lower. But once again, I was told that for our research turbine, actually, when it says it is at 0, there is actually a negative 5.5 offset. So the 0 point is not actually at 0, but negative 5.5. So that explains why at 0 seems to be higher at the 9.6. But still, these are way off from what we expected, and we are still investigating what could be possibly the issue, whether it is with our turbine or it's with the approach. So yeah, exactly. So that's what we've done so far, and yeah, maybe Charlie can take it from there, and if somebody has any question, could ask. Thank you.
Cool. Thanks, Daniel. And it's good that you've managed to get the data in and read, and it's processing something. And so it's nice to see that you've got some results already from the turbine. So a few kind of questions that I've got immediately, and then I can now open it up to the group. So the first is on the frequency of the data. So for OpenOA, the original analysis was all done on 10-minute SCADA data. In this case, what's the frequency of data that
so
you're
our
using?
frequency is like 1 second. Yeah,
Yep.
1 second. So we actually tried different one, but I mean, I had to quickly summarize it. So we could aggregate to 1 minute, 10 minutes. So we did run for different frequencies, but the data's resolution now is 1 hertz, which is 1 second. So yeah.
Yeah, which might be why the power curve looks very noisy, because actually the wind speed measurement might be oscillating quite a bit and your power measurement might be oscillating quite a bit. and perhaps resampling to like, I don't know, 30 seconds or something like that. Maybe it helps.
Yeah, we did for 1 minute.
Oh yeah.
I did for 1 minute, and so I realized because our rated power is 6, so when I resampled to 1 minute, I had few points. So when it comes to the latter part where you have to fit the curve, you realize that you don't have minimum points within the bin, right? And it becomes very difficult to fit the how do you call it, the curve, right? But we could quickly try that. It's not, and that's another reason why I brought it here, so that we could try together. So for instance, if
Yep.
I want to sample at maybe a minute, I could also find the means or
Yeah, that's why you do those changes. I saw a question in the chat from Eugenio asking, does this method rely on the wind speed measured by the cell anemometer? And I can confirm that's a yes. So effectively, the OpenOA analysis has this question mark over it because you're relying on the wind speed measurement that's on the turbine. And we know from experience that actually that wind speed measurement is influenced by the yaw angle itself, or certainly on some turbines, and so maybe on this one as well. We do actually have a second turbine near to this research turbine that we're trying to get data from as well. So we can then use that one as a reference turbine to have an independent measurement effectively of the wind speed or expected power output at the target turbine, which is this one.
so see, like if I sample at 1 minute, already you are seeing an improvement on the curve. Let me apply some filtering to it.
Oh yeah, much smoother curve. Yep.
Yeah, exactly. So we could still play around it, but we try a couple of things, but I mean, I had to present. Still, there are a lot of things that needs to be investigated about that.
Yep. Another question in the chat. How do you know that the turbine was not with a previous static yaw before setting a new static yaw? Did you use a LiDAR to check this?
No. So yeah, exactly. So that is one of the questions we asked. So apparently it was just set in the control system, and we cannot really tell actually whether it's correct or not, really. So now it's a bit inconclusive. We don't know whether since the results we are getting here, it's not what we are expecting, whether it's because of our turbine or because of the methodology used here. So that is another angle that we are investigating.
Yeah, and I'll add two things here. So one is that effectively what we're trying to identify in this challenge is the delta between the known yaw misalignments. So we've got a 0 and we've got a 6. What we think we should be able to measure then is there's a 6-degree difference between the two.
Exactly. And then we are getting something around 3 when we expected 6.
Yeah. And maybe that's linked to the previous question, like, is this influenced by the wind speed measurement being behind the rotary turbine, or is it something else? And then the second to that is if you scroll down to the like curved plots, which show the yaw misalignment. Yes, these ones. So the red dotted line, vertical line, that's where maximum power is achieved. And then the black dotted line is where the turbine is focused on, like where it's where it generally tries to point. So normally you'd expect that to be 0 degrees. In this case, though, then there's an offset to that mean vane angle, which again, maybe it's put there on purpose, because at minus 8.6 degrees in that first plot, that's where you would have expected maximum power. But we're not too sure. So here it's saying a yaw misalignment of 14 degrees because the difference between where the turbine's trying to face and where you get maximum power is 14 degrees. And what you really want is 0.
Just don't tell me. No, probably Cato. I mean, I see one.
I got it.
On Monday.
Thank you for answering my questions, and thank you for sharing the data sets. Are you planning to aggregate more data on these data sets on the near future, or is just this month of data that will be available?
If I understand you correctly, are you asking whether we'll be publishing more data?
Yes.
Yeah, exactly. I mean, where this particular turbine is, there is another one, as Charlie said, for ETH storage. So we would combine both data sets and publish them when they are ready. And I mean, Charlie knows more about this because actually the purpose of the challenge is for this particular presentation, I showed you the yaw offset as we had measured, but subsequent ones we would give data sets without the known yaw offset, and then you would be able to predict what it should be. So yeah, obviously there's going to be additional data sets.
Thank you.
So we're like, this is the first phase of the challenge. We're releasing the data set, the initial data set. Hopefully Daniel can share this code so that others can use it as well. We'll start with it. And then we'll also try and set this up on Renku. Maybe we need to adjust the data set to make it fit in the memory. And then following this initial analysis on the data set where we know, or we're giving everyone access to what the misalignments are, or known offsets are, we'll release another data set which just misses out on that channel. Although we might include a channel to say when the changes have been made. So it's at least everyone knows when the changes were made, so you can then split the data set to find out what they are. Yeah, and that will be the main part of the challenge. But we've kind of done a soft launch here where we're going to release some data and see what people can do with it. Make sure people are comfortable with the data set first.
Yeah, but you want to have like.
Do you have like a scheduler about when this next parts will come out?
Good question. But the initial hope was that we were going to have completed the campaign by now or September. But I reckon in the next couple of months we'll be releasing the data sets. And then so last year we ran a challenge that effectively finished on New Year's Eve. I think it would be nice to do similar so that it comes in the last 3 months of the year when people are like effectively competing to get the best result. So that'll probably be my objective.
Okay, fantastic. Thank you, Charlie.
Cool. Any more questions from the group, either on the analysis or the new challenge?
I mean, I forgot to add something. So really, even how the OpenOA does the analysis, really actually there are one without uncertainty quantification. So I think what I've shown was the ones without uncertainty quantification, but there is actually another one when you do that with the uncertainty quantification, right? And the values change a bit. So that's also this. Maybe Charlie could explain this more really.
Yeah, so from memory, this is like, I think it's termed a bootstrapping method, where basically you exclude some of the data, rerun, exclude some different sets of data, rerun, and then you get lots of results from the same data set, but you're basically using just part of that data set. It looks, when I look at these plots, I'm like, it's got uncertainty in it, but it hasn't captured the uncertainty correctly. Because you'd expect with uncertainty bounds for things to be much like smoother. You wouldn't expect the ups and downs to be so well captured. So that might just be that we don't have enough data in each of the bins to properly capture the full uncertainty. Again, maybe we need to play a bit with the sampling or the filtering.
Yeah, the filtering parameters.
Yeah.
And I also realized that playing with the code, I also realized that usually when I run the simulation or any of them, and I use my default parameters, my own parameters, it runs with the default parameters in the functions, and I don't know why, and I was still investigating. I don't know if you've experienced it before, really.
Oh, have to check that.
Yeah.
If that's happening, then it might be worth opening an issue on the OpenOA GitHub page.
So if you see the plots, I was trying to run for
2 to 6, yeah.
2 to 6, but you see the actual plots. So at first I thought maybe they had hard-coded the bins, but I checked the code and realized no, they hadn't, but somehow it could default to their default values really. But I just found it just like 15 minutes to this, and I haven't investigated it enough, so I would look at it really.
Actually got to enjoy the weather.
Yeah, fair enough. And again, for everyone to know, this is Daniel's like initial bit of work done fairly quickly, I think, in the last week or so. So it's just an introduction to how things can run. Okay, any more questions from the group or comments?
Yeah, that's fine.
Or ideas, really.
Yeah.
Yeah, so I guess.
Okay, so.
As a result.
I suppose one question from me to the group is, would you be interested in participating in this challenge to try and identify static yaw misalignments from the data?
Yeah, I think so. I wouldn't mind playing around with the data and seeing what I can get out of it. So yeah, thanks for the introduction to OpenOA.
Cool, that's good. And I can see a yes from Eugenia as well. How about Eduardo, Ola, Jorge?
Well, I'm just the challenge in Kaggle to predict the wind power, and I don't know if I don't think I have enough time to. Is there any a deadline?
So currently it's in the kind of experimental stage where you can just play with the data.
Okay.
And then the deadline will come when it converts to a true challenge and you're trying to predict the static yaw misalignment deltas. And for that, then I'm suggesting that the deadline is New Year's Eve 2020 6, 25, whatever, that boundary.
25. Okay. And
So till the end of the year, we've got
yeah.
time. And between then and now, we'll have some more calls like this to discuss the data and analysis.
Okay. Okay.
And during that process, the idea is that we do share what we're doing so that we can
Yeah.
learn from each other and so that
Okay,
we can build
okay.
on each other's work.
Yeah. Okay. Yeah, it's really interesting. I think I could do something about it. Yeah. I mean, I want to because as I told you, I'm doing this power prediction thing. I'm just checking that, and I mean, in the end, it's everything connected because everything correlates. I mean, if you are telling me that that there are, I mean, I don't know if I've let me see if I understood properly. I mean, if you are telling me that there are wind speed measuring errors caused by this misalignment, is that right? I mean that they are somehow related.
Yeah. So you have the issue. So
Yes.
the concept here is at a given wind speed, you should get a given power output, and that should be dependent on the yaw misalignment and nothing else, with all things the same. The issue is actually as you misalign your turbine, so if your turbine's at 0 degrees, you get a wind speed measurement of 5 meters a second. But if you just misalign your turbine by 5 degrees, then you actually measure 4.9 meters a second wind speed.
Yes, and that's why, and I understand that's why there was the challenge, this previous challenge in Kaggle to predict the wind speed. Okay, let's say coordinate, your coordinate of a wind turbine based on the other ones. Okay, just to try to figure out how do we avoid this error, this measurement error. Right.
Right. Yep.
And that's what I was telling you when I'm telling you that okay, everything correlates. It's like wow, it's like you need to predict features like pre-machine learning. It's you need to predict features, and they must be really accurate in order to use them to predict now this problem here. No? This your misalignment. I mean, everything it's connected in the end. And okay, I understand now. I mean, I've never worked with this problem really. I mean, I have to study and to document myself about your misalignment and that stuff. No? But I understand that. I mean, all these pointers that all these data points that Daniel was showing of the power curve. Okay, the marked as outliers. The orange points. Yes, go there. Correct. Okay, you see, of course, you see very clear when I mean, for instance, after 6 meters per second, all the blue points on the floor, that's simply the wind turbine out of service. It's in a down state. And you see all these orange points, that is a single wind turbine, right?
Yeah.
Okay, that's yeah, because I've seen this curve. Okay, with the summation or the contribution of all the wind turbines, no, the whole wind farm, But in this case, it's a wind turbine, and you see that all what the I like to do like density plots to see where is normal operation. I don't know if I think. Where do I have something like that?
But for a starter,
wait.
But for a starter, you should know that this is nowhere near normal operation because the filtering here is not done properly, really. Because if
okay,
if you have to do it properly, all those blue below here, below the orange, are not supposed to be part, really. So this is not even close to proper filtering of the data, really.
I get the point. But what I'm trying to tell you is it's very, very, very important to see that raw data like that. I mean, don't before throwing deleting outliers, before doing outliers analysis, okay, it's very important to see all the data points, because in that curve you see the states of the turbine. Okay, as Charlie knows, I am very reliability and risk oriented, so I think of states. Okay, and you know that the S curve, where the higher density of the normal operation, okay, S sigmoid, okay, of the power curve, that would be the normal operation, the highest density, because it's more frequent to find the turbine in normal operation. Okay, and all the data point, for instance, the orange data point, that is a derated generator state, is derated. Okay, the consequences of all this yaw misalignment and errors is the rate production of energy. Okay, so on the floor, everything that's on the floor after nominal wind power, okay, which is, I don't know, 5 point something, everything on the floor blue, it's the turbine is out of service, maybe maintenance, grid conditions, okay, etc. Okay, everything that is orange, oh wow, the turbine is generating power, okay, but really derated. It means, okay, we are having a wind speed of 6 meters per second, a nominal wind speed, but I'm only producing, for instance, 6, and if look at the number 6, and you're only producing 500 watts or 600 watts. I mean, what? It's just the pitch angle are wrong, or we have a condition on the turbine. No? So of course these are outliers, but it doesn't mean that the data is wrong. I mean, they are telling you that the turbine is not operating in a normal condition. No? So that's the thing there. Okay, and normally, yes, that's a more important plot because of the power curve. Okay, and all the weights of every model you fit, okay, are going to point to this relationship here that you are seeing right now. However, there are other predictors, there are other relationships that can influence, no, in the end, it can influence the power generation. Okay, all the models that you fit, even if it's a black box like a neural network, for instance, if you fit whatever model you fit, somewhere the weights of the neural network, the weights of the regression, they are going to signal or try to draw this curve, because the correlation is so powerful. Okay, no, it's physics. No, it comes from the cubic wind speed velocity, 1.5 times CP times area of the wind blades times wind speed to the cubic wind speed. No, that's why you are seeing that. But if you, for instance, in this challenge in Kaggle, where you have to predict the power of one turbine using the power of the other turbines, when you insert a new variable, the power of the other turbines as reference, now you have a very powerful predictor, the power generated by a sister wind turbine, very near of the other. Okay, and everything start to compete. No, the predictors start to compete. Okay, well, it's wind speed measured by the wind turbine, or should I use better the power of the sister turbine? Okay, so that's the thing. That's the thing, and I think it's very important. It's very important to add colors here where you can know when the turbine, for instance, is offline. Every time you have those after 6 meters per second, and when the turbine, there is another state which is weather related, but there is no wind speed. Wind speed is very low before the cut in. Okay, that before they cut in, and that's okay. The turbine is that's normal operation, but but that's weather related. That's it's not enough. I mean, in the SCADA normally they use a labeling system for all these conditions, so you know how to color these points here. No, I think that's important.
Yeah. Correct me if I'm wrong, Daniel, but we don't actually get events or status codes from the turbine in this case.
No, in the data, actually, we have that.
Can you
Oh, we
show me?
do.
Can you show me the tables? Just the CSV or the yeah, there exactly.
Yeah, that's a very fair question.
Okay, so we've got a turbine status
So that's
code. Yep.
So that's why we put this.
So we might be able to
Turbine
filter the data
status.
based on that.
Okay, how many can you run a function to see the unique turbine status available? I mean unique
I think
the
about
vector.
10, about
How
10.
many states do you have, and then you can somehow add an additional categorical variable on your plot, but to see, for instance, how many there are 10, 12, 13. Well, but there is no one and there is no.
So I think it's 13 or 14 because I use are unique. So
Okay.
yeah.
You're going to see if you add that dimension to your plot of the wind of the power curve. If you add this turbine status, maybe you'll see a lot of different colors on the floor after rated wind speed or before cutting. Okay, and you can know that, and then you can filter better your data. Okay, but yes, I mean it's interesting because all this your misalignment, that's going to shift you a little bit the power curve from the high density area of that curve. I suggest you to do a density. Let me see if I have an example here. I don't know. I just because
So we've got the mappings for the status codes as well.
Yeah, I mean,
Yep.
so
okay. Let me see because sorry, I was distracted looking for a plot that I did for other project. Let me see if I can.
so for zero
is operate initialize system. Okay. Feathered position. Okay. What?
So actually 13 different statuses.
Function as one feather standby position. And what's normal? Yeah, I mean jargon. Operating state power production mode up to nominal speed of. Okay, it seems that 10. It seems as 10 is normal operation.
Yeah, so 10 is
And we saw so exactly extract only the filter your data frame where ID equals 10 and plot the curve and compare okay, to see a better without so many other operating states.
outline is right.
Yeah. I mean outliers, but remember outliers from operating state. Okay, I mean remember it's not an anomaly if you can explain it. Okay, so we know that there is a repairing state or out of service because maintenance. Okay, the wind maybe the wind is at 10 meters per second, but the production is 0. But it's not an anomaly. It's in maintenance in repairing state. So I think I did. Let me see if I can share you quickly because I think I published something related to that. I used to publish like small tips on LinkedIn, and I did something regarding the exactly what we are talking right now. Let me see if I get it, I just can't share it with you. Here. Let me see how do I share the link here. Copy link to post.
But if you want to also share, I can stop sharing, then you share.
No, here in the chat window.
Okay.
I think that's my LinkedIn. So you can, and here, I think it's the correct link. Let me check. Oh, it opens a LinkedIn application. Yes, yes. Look at that picture on my on. Let me check.
Wouldn't it be simpler if you share so that everybody can benefit?
I shared the chat window.
Yeah, no, share
Share the screen. Yeah, I think it might be
your
better.
screen.
Do you? Okay, I can share the screen. Sorry. Yes, I can share the screen. Let me share my screen. Wait a minute. It's exactly what we are talking right now. Look at this. But just a plot. And it's not the best plot. I have one better. Let me share my window here. How do I share this? I'm not so familiar with this Zoom share. And which this one, this application here, share. Okay. Are you seeing that?
Yeah, we can see
I
that.
don't know. I'm a little bit clumsy with this stuff. I'm just zooming in. Okay, this is what we are talking right now. Okay, look. Of course, now this is the full output power of Silistea 1. This is a wind farm in Romania, Silistea in Romania, I think. Well, the thing is that's the summation of all the wind turbines. Okay, that's why I asked you. And you see here how I just draw this drawing. You know that okay, full up state. That should be the normal operation, high density here. And you have the rated, which are this point outside, because that means that some turbines are down because that's a whole wind farm. Okay, that's all the turbines, the summation. So it means that some turbines are down or derated. Okay, and you see the floor here, the full down state. That means that there's a grid problem because all turbines are down on the wind farm. Okay, so you can label the condition of your turbine just looking at the summation. For instance, you can see what are full outages of the wind farm. Okay, just zooming all the power curve, all the turbines, and looking the points that are on the floor. No, those are a really strange event because all the turbines are out. Okay, and that's what I'm trying to tell you here with this thing here. It's staying for a single wind turbine. Yeah. Let me stop sharing this thing. Okay. Stop sharing. Okay. Yeah. And there is a better visualization, which is a density. There is a UCG plot, you know. This is this geom density, and you will see when you have high concentration of data points, okay, you will see normal operation always very dense, very dense. You see like the sigmoid.
You might be able to, Daniel, if you just adjust the alpha on your scatter plot.
Alpha, exactly.
Then
transparency.
I think
the transparency.
should,
that's a way to do it.
Should give you a good idea of where most of the points are.
Yeah.
Let me see if I can share you because I have the code here.
And then the other one is, I think you can also, with matplotlib, then you can add scatter quarks to this power curve. And then you can choose like color mapping. So you could base the color mapping on the status codes. What might be good though is we've only got a few minutes left. Is if you could publish or share the code, Daniel, maybe on Renku, give people a link, and then people are able to build on what you've done already and have a play themselves.
Okay, so maybe I'll just upload it onto the Renku space.
Yeah. And then if people can't run it on Renku because it's too big at the moment, then you can still at least have, well, people can still download it and run it
locally.
It's an option. Yeah. Yeah. And I assume for that setup, all people need to do is download the data from Zenodo and then put it in a specific location? Do you want to just share and show
Well,
where that is?
And I think the most important thing is configuring the metadata, so matching the columns to what is expected in OpenOA. And so maybe I'll upload the notebook plus the YAML file where I've done the column mapping, and then we can run it locally.
Yeah, that sounds good. Yep.
Mhm.
Yeah, what we want to do is make it easy for people to
To run
start
it,
off, like to get going. Yep.
Yeah.
Yeah, solve
Let me
the
see if I can show you an example here. We have time. I have to be really quick. And I mean, I'm just looking for density.
maybe I'll just share my screen quickly as well. So I've been talking about Renku. I realized I didn't actually explain what that is. So yeah, if you go to the challenge 4.
Oh, I have the plot. I have the
Challenge 4
plot. Can
here.
I share it?
Just give me one moment.
Okay.
And then
okay,
if you
okay,
go
okay.
to the Renku
Yeah.
space here,
Yeah.
so Renku is this data science platform, so it links to the data sets, and then you can actually link it to a code repository like GitHub as well. In this case, it's already set up
Okay.
with the code, and we can launch a session.
Yeah, because it's weird, we're banging everything around.
It takes long for the session to launch, right?
Yeah, might take a little time. Don't have one. Oh, I do have one. Yeah, there we go. Oh no, still requesting.
Yeah, also.
That's a platform for.
So this lets you connect data sets directly,
Okay,
like from
okay.
Zenodo,
Okay.
and then it lets you run code directly through this platform.
Okay.
So then you don't need to do things locally, like managing packages and those kind of things that sometimes are quite difficult to set up.
Yeah.
If they have an auditing.
Okay. Cool.
So the concept here is if you can do it through this platform, then you can share it with anyone, and anyone
And
just
it's
clicks
going to
the run
work. And it's
button,
going to
it works.
work. Yeah.
Exactly.
Yeah.
That's it.
Yeah. Okay. Yeah.
Yeah.
Like everything containerized.
Effectively. Yep, that's it.
Yeah. Yeah.
Your free sessions almost there.
Well, Sergeant Station. Yeah, that's precisely because maybe it's loading all the. Can I show you just?
Yep, go for it.
It's very fast. I have used to share this, and I have used to share this one. The plot. Yeah. Do you see that?
Yep.
Yep.
That's the turbine one of Hill of Towie. Because so if you see that density, you see the high density point where you have a lot of points, which is in green and yellow. Okay, that's normal operation. That's very frequent operation. Okay, and you see the S curve, and what tends to be purple, that's one wind turbine. Really? Yes. Yes. Yeah, I think it's what I think I have an error there with 1.5 mega, not 2.5 mega. Yeah, and you see the other states of the turbines in the other color. So that's with the alpha, you can do something like that to see, okay, what's normal and what deviates, okay, from normal operation.
Yeah.
Yep. And then here we go. It's loaded, so I'll just show you what it looks like.
Okay.
So yeah, you've got your normal like file explorer here. You can start up your own Python notebook or Python file.
Okay.
This one still needs to be updated with the code that Daniel's running, but we do have a start here at the moment, which has the Kelmarsh analysis. So here you can run the code and it should run without any issues because it's done it for someone else. But we'll update it, or Daniel will update it with his analysis And fingers crossed we can get it to run. Okay.
Okay.
All right. Well, thank you all for joining the call. I need to jump to my next meeting in a moment. So
Wow.
we'll
In a row.
keep working on this project over the next few months. And
Okay, yeah.
yeah, hopefully we'll develop something together that can be used for the industry.
Yes. Perfect. Okay. Thank you, Charlie, for your time. And have a nice day.
Yeah, and thank you, Daniel, for setting things up
Yeah.
and running us through that analysis. Very useful.
Thank you, Daniel, for the
Thank you,
first
Ron.
data
Yeah, thanks,
visualization.
Daniel. Thanks, Charlie.
All right.
Cheers.
Bye-bye.
Goodbye.
Yeah.